Konnichiwa. So today I'm going to be giving a pretty technical talk on the features of the new release Cassandra 1.2 that we're looking at releasing at the end of this year. Over the last couple years, directing the Cassandra project, we've seen phenomenal growth. Our best guess is that we have over 1,000 production deployments of Cassandra today. When you consider that it was adopted into Apache just a couple years ago, this is really amazing growth that we've seen. Really briefly, I wanted to review some of the features in Cassandra today in the stable release of 1.1. We released this in April earlier this year, and some of the highlights of this were starting to improve Cassandra's self-tuning. Starting in the 1.0 release, Cassandra is able to tune its mem table sizes to get the optimal use of your memory. And we extended this in 1.1 to tuning cache sizes as well. I'm going to cover each of these points in just quick detail here. So the row cache is a feature of Cassandra that lets you get speeds comparable to memcached without having to add the complexity of a separate layer to your application stack. So what I'm trying to illustrate here, and for those of you in the back, I'll try to explain the diagram a little bit. But at the top here, the top section here, we've got some data files called SS tables, and we're trying to read a row that has versions of its cells in each of these 3 data files. That's what the orange lines are. That's the row that we're reading. So what the row cache does is, when we pull those lines out in the next diagram below that, where that's labeled merged, we pull those lines out of the data files and we keep the merged version of that row in memory. And so what that lets us do is makes reads much faster when we're reading from the same row repeatedly. So this row cache has been around since Cassandra 0.6, so a very long time. But the new part in 1.1 is being able to tune, self-tune the row cache size. So now in 1.1, you just need to tell Cassandra, use 500 megabytes of memory for the row cache, and it will allocate that to all the different column families that you want cached and adjust those sizes automatically. The next thing that we added in 1.1 is support for mixing solid-state disks with hard disks. So the reason we want to do this is that often within an application you will have data with different performance requirements. So in this example, I have a user sessions table and I have a user activity table. And the user activity table is more of a log of actions that users have taken on my application. And so that tends to be, I'm mostly appending to that. And then occasionally I'll go through and I'll do some aggregation on it, I'll do some analysis of it, but for the most part I'm not doing a lot of reads from that user activity log. On the other hand, the user sessions is getting read from for every page that the user requests. So that's a very high read performance profile there. So what I want to do is I want to on the right side of this slide at the bottom, I want to be able to pin or assign the user activity table to my hard disks that are more cost effective, but not as fast at reads, because I don't need to do as many reads on that. And when I do, it's mostly sequential scans. The user sessions, on the other hand, I want to assign to, in the lower right, I want to assign that to the solid state disks to get the advantage of that random read performance. The last thing I wanted to review from 1.1 is how we've added row-level isolation to Cassandra. And so I've tried to illustrate this by diagramming what happens when you have a read simultaneously with a write in Cassandra. So what I'm doing here in the middle of the slide, I have an update to this row key E29, etc. So I'm updating this row. And at the same time, at the bottom, I'm running a select statement. I'm reading from that row. So what I'm trying to show here is that in the middle, at the bottom, with Cassandra 1.0 that doesn't have row-level isolation, it's possible that I will see part of the old contents of the row and part of the new contents, because I'm updating that row a cell at a time. So there was nothing to lock out the reader while the write was happening. In 1.1, we do provide that isolation. So you will always either see the old version of the row or the new version with all changes applied at once. And we actually do this with lock-free concurrency collections. So I'm not actually doing a heavyweight lock. It's more of an optimistic compare and set based algorithm that we're using there. So that brings us to 1.2, what's coming up next. Currently 1.2, we have 2 betas released. We're probably going to do a release candidate at the beginning of next week. So it's coming along, and we expect it to be done before the end of December. So I'll be going along. Don't worry about copying down all of this. I'm going to be examining these one at a time. And Morishita-san has an entire talk on CQL3 later today in the technical track. So the first thing, and this is something that we've been working on a while, is concurrent schema changes. And we actually wanted to have this ready for 1.1, but we didn't get it quite right. So we had to push it to 1.2 to complete it. But now what I mean by schema changes are adding tables, dropping tables, adding key spaces, adding columns, that kind of thing. So what this lets us do is not have to worry about who else is modifying the schema in the cluster. Everyone can go ahead and create the tables they need and drop them without having to worry about interfering with other people. So what this lets us do is it lets us programmatically create and drop tables and use tables for temporary space, or some people design their application to have a set of tables per customer to isolate each customer's data from the others. So prior to this, you had to be careful that when you were creating a table, nobody else in the cluster was doing so, which was adequate for sort of a static set of tables that you updated when you created a new version of your application and you deployed that. It was okay to do a few changes under controlled circumstances, but this lets us in 1.2 use this feature more powerfully and use it programmatically and not have to worry about the schema conflicts that we had before. A big feature in 1.2 is virtual nodes. So historically, Cassandra has assigned one token to each node. So I might have a token that is assigned this range of the token ring, the F range here. And virtual nodes is going to split that up and spread the range of data that each node is responsible for across the token space. And so what this does is, the reason we want to do this is we want to allow more parallelization of data movement across the cluster. So in this example, on this slide, we're going to rebuild a node that has lost its disks. So we've had to replace node 5 at the bottom in the middle there. So that's why node 5, it's all white. It's lost its data. We're going to replace node 5 and rebuild it from copies that are in the rest of the cluster. So what we're going to do is, node 5 is responsible for ranges C, D, and E. So we're going to copy range C from node 3 in the upper right, and range D from node 4 in the lower left, and range E from node 1 in the upper left. So what we have is, we have 3 nodes participating in the rebuild. So 3 nodes is, in this cluster, 3 nodes is half of the cluster, which is okay, but if we had 100 nodes in the cluster, we would still just have 3 nodes participating. So that's 3% of the cluster now. So this doesn't scale well, this doesn't parallelize well as we add more machines to the cluster, as our cluster grows. So when we split the ranges up more finely with vNodes, with virtual nodes, that allows us to parallelize a lot more. So in this same scenario of rebuilding node 5 with vNodes, everyone in the cluster is able to participate. So I'm using 3 vNodes per range in this example. In practice, the default is to have 256 vNodes per range. And that's actually one of the improvements we've made over other implementations of the vNode idea, is that our implementation allows you to grow the number of vNodes per machine if necessary. So that's useful in 2 ways. First of all, it allows us to upgrade from a 1.1 or 1.0 cluster to a 1.2, and then turn on vNodes and shuffle the vNodes around the cluster. So you can upgrade from an existing cluster with no downtime and deploy the vNode improvement across your cluster. And then secondarily, if your cluster needs to scale to hundreds or thousands of nodes, and now 256 vNodes is not enough to get good randomization of load balancing, then you can increase that at a later time as well, if necessary. So another thing, and backing up just a second, I wanted to point out that I have a category of features here on the left. Halfway down, this category is the support for fat nodes. So fat nodes is what I call machines with tens of terabytes of storage and more than 32 gigabytes of RAM. So increasingly, It's very easy to deploy machines with lots of disk space, lots of RAM, lots of CPU cores, and so we're improving our support for this in Cassandra 1.2. So part of that, the first one of those is support, better support for JBOD configurations. So JBOD, of course, stands for just a bunch of disks, as opposed to RAID. So what we want to do is, we want Cassandra to be able to manage the pool of disks attached to each machine without having to duplicate data with RAID. Because Cassandra is already replicating your data across the cluster. You know, typically we use 3 copies of data in a Cassandra cluster. So there's no reason for me to give up half of my disk space to RAID. I shouldn't have to do that. But historically, Cassandra has not understood how to deal with a disk going bad. So this is what we've added to Cassandra 1.2, that if I have, in this example, I have 4 disks associated with this Cassandra instance. So if disk 2 dies, Cassandra is now able to recognize that and route data away from it to the other disks that remain good. So at this point, what I would do is I could replace disk 2, or I could even leave it alone and just tell Cassandra to go ahead and repair yourself and just put the new copies of the data on the remaining 3 disks. We're also continuing to move data structures off heap. So what this is referring to is the heap managed by the Java virtual machine is limited to 8 to 16 gigabytes is a heap size that Java can deal with relatively well. Past that, and your garbage collection times start getting really painful. So we want to keep heap sizes down. But Cassandra's storage engine needs to use memory proportional to the size of your data. So that's what I'm talking about here. I talked about SS tables earlier, our data files that we store rows in. Each data file has a Bloom filter associated with it, which is a probabilistic set that lets us know which rows are in which data file. And so this is proportional to the number of rows we have. Similarly, we added transparent compression to Cassandra back in 1.0, and the compression metadata also takes up space proportional to the amount of data we have in the data files. So we've moved both of those off heap in Cassandra 1.2, so that allows us to keep heap sizes down and manageable. The next feature that I wanted to discuss is atomic batches. So first I'll review briefly what a regular batch is. A regular batch is just when a client tells Cassandra that it wants to update multiple rows at the same time. So here on the left, the client has 3 rows that it's updating that I've colored red, yellow, and blue. So the client will give those to a Cassandra node that we call the coordinator, and that will send out the rows to whatever replicas are responsible for those. So this works great, except that there is a corner case that's problematic. And that is, what happens if the coordinator dies after it starts writing the rows, but before it finishes. So in this case, it's written out the red and yellow rows, but not the blue. So I have a partially complete batch. So historically, we've said that it's the responsibility of the client to retry that write to a different coordinator and let a new coordinator finish that batch. But that's not really fair to the client. This is something that the server should be responsible for completing. So what we've done in 1.2 is we've added the concept of a commit log for batches. So it's a distributed commit log that we call the batch log. So at the bottom of the slide here, you can see what we do is whenever there's an atomic batch, the coordinator will write the entire batch to the batch log. And then if the batch log node detects that the coordinator died without finishing the batch, it will take care of finishing that. So we get atomicity, which means that if any of the rows are successful, then we guarantee that we will complete all of them. But it's not isolated. So I can read the red row before the yellow and blue node rows are written. So I'm not providing isolation, but I am giving you atomicity. As I mentioned, there's a complete talk on CQL later today, but just really briefly, CQL is the future of development with Cassandra. We've historically had an RPC-based client API based on a library called Thrift that's been unsatisfactory for a few reasons. So we're moving to a CQL language, the Cassandra query language, which is essentially a subset of SQL specialized for Cassandra. On this slide, I have 3 statements. I have create table, create index, and select. These are all valid in both SQL as well as CQL. But we're not trying to make Cassandra into an analytical database or an RDBMS. It's still focused on what Cassandra is good at, which is scaling. So we're still focusing on denormalization instead of distributed joins, limited support for order by, limited support for aggregation. So it's still Cassandra under the hood. We're just exposing that functionality with a more friendly query language. Incidentally, CQL also supports prepared statements. And with prepared statements, CQL is about 10% faster than the old Thrift API. So we get extra performance out of this as well. So I want to quickly explain how we map Cassandra column families to CQL tables. So there's three examples that I want to cover. We're going to pretend we have an application that deals with music and songs and lets users create playlists of those songs. And we also want to allow them to tag songs with different metadata. So first of all, I want to record, for every song, I want to record the title and the album and the artist, as well as I want to have the body of the song as an MP3 or a lossless encoding of that music. So this is at the top of the slide. I have how I would declare this column family using the Cassandra, the old command line interface. So this is not CQL yet. This is the old command line interface. And then at the bottom, I have 3 example rows of song data in that column family. So in CQL, this actually translates very straightforwardly to CQL because I have each row has a song title, each row has an artist, each row has an album. So the data in those rows, it looks like an SQL table already because they have the same columns in each row. The song tags data is going to be more interesting though, because here this is what we call in Cassandra a wide row. So each row will have different cells in it this time. So what I'm doing here is I'm using the cell name, I'm using that to contain the tag that's associated with the song. So I have cell names blues and 1973 associated with ZZ Top song from earlier. And then I also have another song with tags covers and 2003. So I don't actually use the cell value at all in this example. So the question is, how do we map this to a relational table kind of way of looking at the data for CQL? So this is what we do. In CQL, we would define the table this way. The important part here is that I'm using a compound primary key. So that tells Cassandra that the data in the column family is going to correspond to the way we present it as a table like this, that the cell name of each row, each cell name is going to correspond to a column called tag name. So that's what I've tried to diagram with the arrows here, that I'm taking those cell names and I'm kind of stacking them vertically into this table so that each column, or rather each cell in the column family becomes a row. So the column family row becomes 2 rows in the CQL table. So what in CQL terminology, we would call that storage engine row, we call that a partition. So the partition key is the first element of the primary key statement. So I have primary key first ID, so that's my partition key, which is the storage engine row. And then I have tag name, which is what the cell name gets mapped to in the CQL rows. And then finally, we're going to have playlists. And here we've denormalized the song information into the playlist entries. Because remember, we don't want to do joins, so we're going to denormalize that information here. And the way we do that is by using a composite type to tell Cassandra that the cell name is going to be composed of 3 pieces of information: the artist, the title, and the album. So this is how I've diagrammed this with the old command line interface. So when we move to CQL, we're going to take those 3 pieces of that cell name and split them up into 3 different columns like this. So we're mapping the title component to a title column, and the artist component to an artist column, and so forth. So this is how we do that in the declaration, where we give it, and we're still giving it a compound primary key, and all of those pieces of the composite type are part of the primary key, and that tells it to map it to these columns in CQL. So again, each cell in the column family row becomes its own row in the CQL transposition. And if this is the hardest part for people to wrap their minds around with CQL3. So if this feels foreign, then you're not alone. This is hard for everyone. So we'll go over this more in the CQL talk this afternoon. But for now, I just wanted to start that percolating in your minds. The last thing I wanted to talk about with respect to data modeling in CQL is that Cassandra will sort or cluster the data within a partition, which is to say within a storage engine row. So in the playlist example, this wasn't really important, but sometimes it can be very important to have a specific ordering on your data. And so this is useful for time series, and it's also useful for user activity graphs. So in this next example, I have a Twitter clone. So I have users make tweets or messages, and users follow other users. So the main query I want to make is, show me the messages that my friends have posted. And I want to see those in chronological order. I want to see the most recent ones first. So the way I would do that in Cassandra is I would create a timeline table. I would denormalize the messages into that. So every time I post a message, I would insert one row into the timeline table for each friend who is following me. So then when I go to ask, show me all the messages made by the friends of DriftX in this example, then all I have to do is find the DriftX partition, and I can scan through it because Cassandra takes care of ordering the messages by the time they were posted, which is why I have the tweet ID in orange here. That's a version 1 UUID, so it has a time-based component, and I can sort based on that time to get messages in chronological order. As part of improving the support for CQL in 1.2, we've also added or started a data dictionary. So this is where Cassandra keeps information about itself and exposes that as CQL tables. So the top level of Cassandra schema is the key space. So I can ask Cassandra, show me everything about all the key spaces that are defined, and it will list those for you. Notice that I'm in the system key space when I'm doing these queries. That's where all the data dictionary information lives. We can also ask it, show me the information about the column families and about the columns that are defined in the column families. And I won't show the output there because there's lots more columns there, and it doesn't really fit on the slide. But you can definitely try that out. Another interesting thing that we expose is information about the local node. So there's actually just a single row in this table, which is the local row, and then it tells you what data center am I in, this is actually an interesting one. The last column here, so you can read through the list of column names, the last one is truncated act. So what we've done in 1.2 is for every column family, when you truncate it, which tells Cassandra, throw away all the data in this column family. When you truncate it, we actually record that time that you truncated it in the column, in the data dictionary, which lets us avoid replaying that data when you restart. So if you have a bunch of inserts that are in your commit log and you truncate that, if you restart your node, we want Cassandra to know, ignore these rows in the commit log when I'm restarting. So that's what that's doing. Before 1.2, we would actually force out all the commit log entries, which means we'd have to flush every column family in the system to be able to remove the data from the commit log physically, which is a much more expensive operation. So this is one way that we've optimized truncate in 1.2. We also have a table called peers that gives us more information about the other nodes in the cluster. It says, what does this node know about the other nodes in the cluster? The last thing I want to talk about that we introduced in 1.2 is request tracing. So what this does is you tell the CQL shell, or you tell the Cassandra client that you want Cassandra to trace the next request, which is in CQL shell, you do that by saying tracing on. And then whenever I do a request after that, as you'll get information like this after you do an insert or a select and so forth. So the fun part about tracing is that it collects information from the entire cluster that deals with your request. So in this example, my request starts on localhost, which is 127.0.0.1, but the data actually lives on another node in the cluster, which is 0.2. So you can see in blue, the blue lines are the lines from the coordinator, and then the red ones are the ones from the replica node that actually store the data on it. And so the request starts on the coordinator, it sends it to the replica replies back to the coordinator, and the coordinator tells the client, okay, we're done. So in this case, we're just doing a simple insert. It's pretty straightforward, but tracing can actually help you troubleshoot or understand what's going on to cause performance problems. So in this case, I'm going to give an example of an anti-pattern, which is to say something people do a lot that isn't a very good idea. So a lot of times, because Cassandra will do clustering within a partition, people will think, I can use a partition as a queue. I can put events or objects into this queue and pull them off of the front, and Cassandra will give me ordering for free, and this will work great. But it actually doesn't work great because, and so here's where we're doing the clustering. We're clustering on the created at column. But what happens is, as I pull items off of the queue, when you do a delete in Cassandra, the data, the disk space isn't reclaimed instantly. We have to write a tombstone and keep that tombstone around so we can make sure that every replica in the cluster knows that the row is deleted. So that's what I'm representing here with the lines through the rows, that I've pulled that object out of the queue and I've deleted it, but there's still a tombstone there that Cassandra has to read through when you ask it for, give me the next object in the queue. So this is a trace from after I inserted 100,000 items into the queue and then deleted all of them. So when I do my select query at the top here, select from queues where ID is my queue, and then order by created at limit 1. So that would be give me the next item in the queue. And then this is slow. Now this takes 35 milliseconds, which for Cassandra is slow. And you can see where that time is coming from the trace. In the green row that I've highlighted, it says read 1 live cells and 100,000 tombstoned. And that's what took almost all of the time in the trace, is that it had to skip past all those tombstones before it found the live one. So if you're dealing with a situation in your application where queries are taking longer than you think they should, then request tracing can help you figure out what's going on, what's causing that. One other thing that this shows is how it shows where we can improve Cassandra with respect to latency performance. So there was a benchmark done by some academics in Canada. They published a paper at the Very Large Databases Conference earlier this year. And they benchmarked Cassandra against HBase and against VoltDB and against Redis and against some other databases. And they did a lot of different workloads, and they were primarily looking at throughput and latency. So in the upper left is the throughput graph, which is mostly covered up, but the line that's going straight up diagonally across the graph, that's Cassandra. So you can see that all the other databases are much slower throughput-wise than Cassandra, which is great as long as you're using Cassandra. But in the latency studies, they got results that look more like this. In the lower right, Cassandra is the solid line that's the second from the top on most of these. So on this graph, higher is worse. So Cassandra's latency is actually higher than most of the other databases. And this is why tracing actually shows us where that latency is coming from. Cassandra uses a staged design inside the storage engine for processing requests. So you can see that from the stage where it determines the replicas for mutation to sending the message, there's actually no additional computation that needed to be done there. That's just Cassandra handing it from one thread pool to another. And that took over 200 microseconds. And similarly on the replica node, between receiving the message and applying the mutation, again, that's just going from one stage to another. And that took another almost 200 microseconds. So I've circled in red, each of these places are places where I'm not doing extra processing, but I'm losing time moving from one stage to another. So, this is highlighting a way that, a place where Cassandra has room to improve. So this is going to be something that we're going to be working on for the releases after 1.2. I think I have time for a couple questions. How much? Let's see. Do I have 10 minutes? 5 minutes?
No problem. 10 minutes.
Okay.
何か、質問ある方、挙手いただけたらマイク持ってきます。後ろの方いらっしゃいますか。
That must have.
はい。今日のトークと関係なければ。大丈夫だと思います。
I have a question about Java virtual machine. This is not related to today's talk, but I have a question about Java virtual machines. In the default, we are using Oracle Java JVM, right? But there are some they call high performance Java virtual machine, commercial machine in the market. You know?
Yes, so we've occasionally recommended to customers that they explore using Azul's Zing JVM, whose main benefit is very low pause times for garbage collection. So we've done a lot of work with Cassandra to avoid fragmenting the heap and avoiding stop the world garbage collections in the concurrent mark sweep collection. But there's the new generation collections are also stop the world. They're just shorter. But those will still be 50 to 100 milliseconds when the Oracle JVM needs to collect the new generation. Zing will consistently get those under 10 milliseconds. So if you need very low variance in your request latencies, then Zing can help you get that.
Okay, thank you.
いらっしゃいますか。
はい、ありがとうございます。